I can talk a bit about, yeah. So basically, we're going to start off. Sorry, exactly where we left off to last time, because I have done absolutely zero coding on this in the past 2 weeks. I've been geeking a bit about mathy stuff though. um, you know, some type of theory there. There's an article by Mike Schulman that I want to read that might be relevant. I am still quite concerned about the issue with quotient types. The fact that as things are set up right now, thank you Twitch, as uh, as things are set up right now, like a term can be a member of different quotient types or different types that have like different equalities, and this is going to make the life of a congruence closure algorithm really really hard. um, I don't exactly know what I want to do right now about this. um, yeah, I don't know. I like it to be easier to work with than working with Setoids and Coq or something like this. Um, in a type theory that supports quotients correctly, you're supposed to be able to just do some rewriting up to that. Just use the equality, and it just passes automatically under everything. And here it might be a bit harder, but I haven't found a solution to make things a bit more rigid without compromising the entire design of the system, which in particular replaces any notion of like equivalence up to computation in times by equality, which is one thing I was quite looking for. One of the reasons why I wanted to explore this, by the way, is because computation in types and linear types don't, I'm not entirely sure, mesh very well. Um, the system I came up with that does like full classical linear logic with different types um, uh, is based on polarized logic, and so it's called by value, and computation type is not entirely clear. Though the Trustlight folk at UQTT, as well as Edwin Brady, may not need that. So I don't know. Maybe I'm just being overly conservative. I have no idea. But that was the reason I wanted to see what I can do without pre-existing computation in types. Well, that was one of the reasons. Anyway, let's get started. So last week we left off and we had a wrong proof, an incorrect proof. So we're going to fix this. Somewhere around there. So these proofs shouldn't work, I think. I have proof commutativity of addition. That's fantastic. Wrongly. Okay, so the problem that we had was that seems that in some cases the system cannot distinguish between between a failed proof and a completed proof, which is unfortunate. So I want to get back at where that probably was. Boom, 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 boom. There's a bit repeat intro use induction, alternative, subsumption, Darling I-type, unification. And that's probably higher than this, isn't it? Res M. Success or failure goal, right. Oh, that's my monad, but my run is not here. That's fine. So it's somewhere else. How big is that file already? 800 lines. Not that much. It's a bit of a mess. There's a lot that could be factored. Goal, PP goal, PP attempted goals, run TCM. Try discharge. What is this? That's the one. Discharge status. Yeah. Prove with M0. That's all fine. So what is actually the matter here? So my point was that these were definitely like wrong. Like they still type check, don't they? No, they don't. Wait. Oh. So maybe they're not wrong. Oh. This is more surprising. Sorry. But it becomes wrong when I do this. Oh yeah, because I get an error that I can't solve it. Right. So here seems to be happening is that we get it. Well, actually, this one is the wrong one. I think. Because now we have an error somehow. Why do we have an error? It's just weird. Let's try to figure this out anyway. Yeah. We'll wake my brain up and we'll just find out, shall we? Tick tack 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 tick tack 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 tack. Because use is right. Use can do an error if what was it? No, use shouldn't return an error anytime, does it? Ensuring that's not an error, so just returns a sub goal every time. Oh no. If there's if I don't have an X available, not the X, the if I don't have the thing, if I misnamed the thing, it goes to an error. But otherwise, we'll improve on it. But I don't know. I remember doing something that was fishy where I took a bunch of things and reduced it to a list. That's probably somewhere here. So it's Torres charge. RT prove with access proved equals G discharge G open. Yeah. And then so what do I call run TCM? In two places. Okay. Oh yeah. So I'm concerned about this one. Type checking position, I emit a bunch of P things. MTags. Apply MTags. What does that do? Yeah, that's the thing I remembered was being weird. Okay, fantastic. Got to cut the mic for a second. Okay. So what's happening? I haven't figured it out yet. Here. So that is not a problem. It just does apply type. So here we have a bunch of goal to such status, and we have a list of goal here. And we get green on the thing, which I'm probably not pointing out. What am I pointing out when I do this? You don't even see me pointing. I point more or less in the right direction there. Fantastic. By the way, I've made some like I've studied a bit of OBS Studio today. I randomly, for like half an hour. I discovered there's a couple of cool things that may help me improve my setup in the coming weeks, just a little. So we might have a slightly better setup. I'll attempt it. I'll play with it anyway. Sometimes, maybe, when I'm bored. So here we have this interacted goals, and we do PP attempted goals, interacted goals. Interacted goals are of type goal discharge status, and a list of goals. For each goal, right? And so it was already discharged, we discharge. And if it was open, I apply one, and yada yada. And when I apply one, I keep open because it was already open. Get the new status from this, and the status is: does there exist a list? Why? What have I done? Where does apply come from? So that is wrong. Okay. Okay. So what is apply? B. Right. So that is just wrong. So I should return a maybe least goal. Like, let's do something cheap. Do I use apply in a lot of places? No, just there. So when if it's a failure, I need to return that as a failure. But I can't like, that can be an empty list failure. So I'm gonna do this and this. And okay, and then I'm just gonna follow the type error. Turn Dante on. What? Oh yeah, there's an error here already because I want to do maybe here. Really? Okay, that was just being slow. Okay, and here I have to say nothing discharge. Uh, let's do status remaining. We're going to call that res. It's a terrible name, doesn't matter. Res of nothing is oops. Empty. And so here is just of a list. Oops. Open. Okay, now we have an error. Fantastic. Doesn't tell me why, because it probably comes from a function that I don't know where. We can search for M0 now. At least we fixed that bug. No more. I can just make a fix up thing, I guess. It's just a fix up of this. Oh. Well. Oops. Oh yeah, I was editing Git under the buffer that you can't see, but that's fine. I'm displaying properly and legibly a setup. So now I have something that doesn't work, and I don't know why yet. But in order to know that, we're going to chase for the M0s. There's not a lot. Intro, compose M0. So there's I need to check how I signal failure. I probably have a function do fail. So I need to replace that by do fail. Do fail. Let me use $. And do fail takes a G. So there you have it. And then it's oops. The next one here again do fail of G. That is fascinating. Oh, no, it's not a nem anymore. It's my resem, which is fair. Okay, so yeah, there's no... I was wondering if there was an A somewhere. Still doesn't work. Compose reader T. Why, what, why? Oh, it is. Correct. And that because there was a name, right? This tack. In this tachem, but I guess I just need to say there's a tack. It's a tacky name. Okay. Again, here, max intros is a tag. It is a tacky name, though. Use already was one. Is there any other M0s? There's another M0. But I think this one is fine. I can't read my screen anymore. That was a very, very smart way to display things. Yeah, so proofs are interactive only in a way. I guess we could like, I don't know, like make a REPL or something. But I don't know how to do this in a way that would be convenient. So now none of the ghouls can be. Oh yeah, the ghouls are reversed. I need to address that too. I need to figure out why I reversed the ghoul. I had So the one on the bottom is the one on the top, and it should and yeah, and the one top just probably lacks a don, I think. Oops. No, it was not that. Okay. So what? So on the bottom, I know that plus x0 equals x, and there's no plus 0x. Oh yeah, theorems don't have names. Oops. What a night. I probably could have done that overnight. It is not going to be exciting. Yeah, there's something. So, yeah. Error messages. I'm just going to pack everything into a single comment at the end. It's not interesting enough to split. Refined. So now I need to add a name to theorems, I think. Where are my theorems? Okay, here are my theorems. And now someone isn't happy. What? Oops. Okay, I can't. Syntax error. You what now? Oh, okay, yeah. There's a syntax error in my thingy, indeed. In main, of course. No more flag check errors. Whoa. Here we go. Just yeah, there's no locations. There's probably a way to get locations, but I don't know what it is. So just have to look at the theorems. So I guess that is plus a sock. The names could be correlative, but whatever. Plus 0x. These are fantastic names, by the way. I'm not sure I should use colon as the symbol for that, because contrary to the proofs as propositions as type thing. Plus sucks x. Is that the? Oops, that will not work for sure. But yeah, I need the colon here. A proof is definitely not the same as a term in this. And now I've got really. I don't know why it's now I've got a name So that was called Z. Okay. Um, Now I solved one of the two goals. That's great. Names for theorems. So now to prove commutativity, have this thing. I proved that plus sucks is sucks of plus xy plus x sucks y is sucks plus xy. I know that plus xy. I need a couple more. Least for all x is annoying. I don't think I need it. Okay, I don't need it. That's better. So I need a couple more of these. Oops. And now we're done. Well, that is not an elegant proof, but I don't know way around this. Okay, so now we have fixed our commit. So now, and so we are going to base all of this and make a clean commit. I'm going to pick this up. These are all fix-ups. I'm going to squash with this. I'm just deleting this, and this is going to be what I said, just enough tactics. Push force to the branch. Give me a sec. Okay. Good. I could make a pull request of this, but we don't necessarily need to. What I want to do now is change a couple of things. I want to replace my users of views by users of what do I want exactly? I want a few more things. I think I want to remove the this part of the induction, just prove by induction. But we are going to add ourselves a couple of things. Have places where I'm going to replace use by have, but have we'll be able to use any number of things. So we can do using any number of theorems. Can use subsumption. So let's do this. So let's go where use is. We don't necessarily need this. I'm going to keep it around, but we don't need it, I think. So we can just have... I think like definitely we want eventually... what we want eventually is a real sequent calculus and justify maybe something like congruence closure could be just a primitive, but most of the things like the should be built out of some like one sequent calculus, and we just compose them like a bit simpler. But I don't know exactly how I would like to do this. So it's going to evolve. Have, it's not term, I want a proposition, which eventually is going to be a term, I guess, but it takes like a P and a K, G at goal, hips, concal, compose. No, I want to be able to use a bunch of things. So I want a list of items here. So lems. $do. So what we want to do is let's do have zero. Have zero. A simple tactic. And or subgoal. Well, I have two subgoals actually. Like, you know, we have a side condition, which is goal, P column hips concal. So we've added P, and we just want, that's the side condition we want. The idea is that have is say, no, sorry. Have, that's not the side condition, that's my sub. So my side condition is that this is true. And so in my side conditions, I have my hypothesis. And so in have zero, I don't have the lems. Just do this. We don't need to define everything as primitive tactics. Probably define too many primitives already. So we define two different goals. One is the side condition that I can prove P, and one is my subgoal, my main subgoal, which is goal P colon hips. Like I can prove my conclusion, assuming P. In. I don't like this. Oh, it's not a hint. It's not an in anyway because I'm a do block, which means that it might not that. I don't know how do block lets align. I get lost all the time. So what we want to do is a bit of compose. Proved sub. I want the side condition first. I guess I do. I'm just going to call it side, otherwise it's going to just be very long. Proved side prime, proved subprime. Subprime. It was not funny last time either. Side prime equals side prime. Dollar entering subprime equals sub. I should do the same order everywhere. This just checking equality thing is bothering me. I need to check that. Like, if someone knows how Isabel implements these sort of things, like verifying that the goal that you get are indeed of the right shape. Well, you might not always need it because you might just apply a transformation on the goals you get and just suppose that. Just check at the end. I don't know how Isabel does that. I'd like to know. Prove G. Yeah. Apply to. It's a real mouthful. I forgot. Oops. Dollar here. So here, I'm going to do this. Dollar K side star K sub. That type check. It does. Now we can define have, takes a prop in a list of ident. And so in stack, and have is implemented by calling have 0, and then that distribute dispatch. So dispatch, tactic to dispatch, I guess, followed by a list. The second element of the list is tactic.id. Oops, interesting. And the first element of the list is my discharge tactic. And there's going to be an error if the discharge tactic doesn't complete the goal, which I'm not sure. Well, I know how to do, but I should probably have. I guess it's a bit complicated if I need a failure thing to do. So yeah. So my point was, oops, it's the wrong place for my V. What have I done? Where discharge is a tactic Uh, uh, so it's going to do use. I'm just trying to figure out. So that's discharges use it one, then use it two, then oops. At the end, it's a then and fail. And oops. Something like this. And that, which one is it? It is full there. Fantastic. Discharge. I leave the order in which I implement, I add things. It doesn't matter that much. What matters is that fail is last. Then is not associative. That sort of matters. Discharge equals fold L. So it's going to be it's going to be what? I'm getting an ident as my first element. Well, that's lem. That's lem. And we get attack. And attack is the right hand side. So we do use lem mt then tactic then tack applied to fail. Actually, it's not applied to fail. It's applied to done because I'm not. It's called discharge, but it's the discharge tactic, so I shouldn't call that discharge. I should call it something else. Or like discharge with. That could actually be a fairly standard thing. So let's make it a discharge with function. That's fantastically interesting. I was not trying to write a T and I didn't type that by reflex. They just, the T was a typo and the I was me trying to move up, which is my on my modal keyboard. Well, not keyboard, but like key calls, I guess. So that takes a bunch of lambs and that returns. I wrote full L instead of full dar though. That's interesting. I wouldn't have type checked. Lambs. Whoa. So now we have, so I'm going to make syntax for it. have tag x per 1 colon equals have followed by a proposition. How do I type proposition? I type prop followed by using, and then I want a list of items. Oh, did I have that? These are terms, but I just want a list of items. Do I have a list of item thing? Ah, damn it. No, I don't. So I want a list of items separated by commas. So that's the syntax. I cheated so much. I guess I can have it here because it's related to really? Oh yeah, I forgot a semicolon. It is not exhaustive. Here it is. You have problems. Have problems. Okay. Now we're going to start using it. Plus xy 0 with we can do have plus y 0 equals y using and it fails. I'm going to commit the rest. So in main, I'm not going to commit that particular line where I'm working because I want to be able to possibly revert it or look what I did with have. Okay, so it broke everything. Plus x0 was y. What did I write? Okay, I wrote w, so that was not going to work. Okay, and here we're saying have plus xy 0 plus xy plus 0 equals plus xy using plus x0. Before has plus plus. Oh, has. Interesting. Okay. tea. I need some. I need to be a tad careful. It is very full. In addition, it is still steaming hot, so I don't want to hurt myself. Probably. Boop, boop, boop. Boop, 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 boop. Boop, boop, boo. Boo. Boo, 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 boo. We might want a better syntax than this. The one in the grand scheme of things, it's just a highlighting problem. Okay. So we say have plus xy and sucks of z equals sucks of plus xy and z using plus x sucks. We're using plus x suck a lot, so we could just use it once and have plus y sucks z. What is happening? Equals sucks plus yz using still works, I think. Yeah. At some point this is going to be unwieldy and we'll have to find some way to display this. Have plus x sucks of plus yz equals sucks of plus x plus yz using still works. Have plus 0 sucks x equals sucks of plus 0x using plus x sucks. Yeah, I don't know. It's not fantastically readable, but it's okay. Have plus x0 equals x using plus x0, oops, have plus sucks x 0 equals sucks x using plus x 0. My error messages are still inexistent, which is going to be a problem eventually. Have plus x sucks y equals sucks plus xy using it still works. We're still bring the trivial things though. Have plus sucks x y equals sucks plus xy using. Here we see very well what the proof is doing, which is cool. And I broke everything. When did I broke everything? When did I? Oh, I see. No, I don't. That is not what I was proving, was it? Plus x sucks x. Oh. No. I'm confused. Oh, I see. Okay. That's because it sucks x sucks y. And here it still sucks s. So no, it's not as evident as what I was saying. Okay. Everything green. Green ticks everywhere. What's happening? Actually, that was correct. Whip. We still have to do commutativity. So here we were saying have plus x0 equals x using plus x0 have plus 0x equals x using I think many of these rules we could put inside the system, like register them for the congruence closure to run them. Could be a bit costly, but might work. Have plus x sucks y equals sucks plus x y using okay, we're good. Have plus y sucks x equals sucks plus yx using the goal here was to prove that plus sucks y equals plus x and sucks x plus sucks y equals x. We're saying, oh well, x and sucks y is the same as sucks of plus xy, which is the same as plus y sucks s. We could do a chain of reasoning, I guess. I'm going to do something actually, but I'll change in a second. Here, because I'd rather be mechanistic for the time being, success y equals sucks plus y plus xy using plus x sucks plus sucks x the printing of tactic is just a bunch of blah. Have plus sucks y x sucks y and x equals sucks of plus y x using, we're getting there, using plus sucks x, and we are done with this, and we're going to do a bit of ordering. Ooh. Checking something. Okay, so we say, okay, our goal at the beginning of the day is to prove that plus sucks xy is the same as that plus x plus sucks y equals sucks y plus x. So plus sucks xy is the same as sucks plus xy, which is the same as sucks of plus yx, of course. Because we know that xy is, we know that this is the same as plus xy. The point is, good sucks plus xy, we can say, oh, I can bring, what do I want to do? I don't need all that, do I? So this is plus yx, I already know. I don't need to add it. So I can say, oh, it's we can say, for instance, have plus xy plus xy equals plus sucks yx using oops, no, trying to be clever and failing. This is not, this is, okay, that was completely useless. That is because sucks yx is obtained by using plus sucks x. Doesn't like me. Oh yeah. No, actually, why not? Oh yeah, okay. The problem we have here is that I need an instance of it. Otherwise, it just doesn't recognize that this is what I'm doing. So I need to be very explicit about this. That being said, this would be the one. What I'm claiming is that these two are unnecessary, are they? Yeah, okay. That was just easier than I thought. So you just take the y out, take the what back in, but you have to use the same form as the lemmas, which is unfortunate. Instead, we might want some kind of grounding for lemmas. I don't exactly know what we want. Like, honestly, fascinating. So the trick here is it looks slightly readable, but we can't really do everything. This needs to be an instance of one of these things, and this only of one really. Right now, or all these could be directly interpretable by the congruence closure, which I think we should probably have something like for alls uh, followed by an equality. We might just want to interpret them as a bunch of equality rules for all the things that match, for all the variables that match at least. But we might want to have all the terms as well. I'm not exactly sure how to do that grounding. It might be big. In which case we would not need. So that would just the subsumption thing is just an optimization, which I don't even remember why I introduced, but that was important. I know, and maybe all these rules that are directly interpretable by the congruence closure are just like that. So in classical logic, like every rule that is propositional that doesn't have a for all or an exist is interpretable by the congruence closure. We could add for alls by just doing some grounding. Yeah, which I don't know exactly how to do well. And we could, but the difficult case, well, existentials, of course, just like you can't do anything with them. Well, I mean, kind of existential. You just say, okay, it's an existential, so I'm going to. Well, the problem, yeah, the problem with grounding is at any rate, the proposition like the Hairbrand term and equality, that's called first order logic, or first order logic with equality, but that's the normal form and it's undecidable even for classical logic. So even like and yeah, just the for alls are sufficient to mess everything up. I think the exists are not that hard actually. Just introduce a new name, and so it's not very useful. But okay, that works. But um, but for alls are hard because you can have infinitely many instantiation. Like if you have something like x equals f of x or something silly like that, then you could ground for every possible thing. Like you have x equals f of x and f of x equals f of x and f of x is equals of f of f, etc. And if there's a g that works, it could be g of a of f like stupid things. And so it's not necessarily clear what to do with for alls really in general. And in intuitionistic logic, another problem is the implication clause. In classical logic, you would just transform the implication clause into not A or B. So you'd say, okay, it just got two branches. I prove A implies B. So when I have A imply B, I just have to prove two things, like that B implies the conclusion, or entails the conclusion, and that not A also entails the conclusion. and that's all. But in intuitionistic logic, this is not correct, as far as I know. So you would need to prove that you can prove, like you have A implies B, you would need to prove that you can prove A, and that knowing B, or that you can ignore. So you have two choices: either in ignoring or being able to prove B, and then you get A, which implies some backtracking, but might still be decidable. I haven't thought about that. This is intuitionistic just because I don't know. I'm more used to this. It doesn't really need to be. I could just decide that quality is always decidable or something like this. Um, for now, it won't last very long. But yeah, so handling these for all thingies is somewhat tricky. Getting a good, reasonable proof system. You don't want a complex one, really. You want a simple proof system that just does something that you can eyeball. They can just write proofs more or less like you would prove them. And I also like probably to remove the intros thing, but never mind this. I've got a few ideas about that, but it's for later. The general point being, I probably want this to prove a bit more things eventually, but I don't know how to do this. It's something for people. It's more like proof automation than. Pick. Okay. The real big question is, what do we prove next? I guess we introduce multiplication. Fun fact thingy. Let's see where we go with this. Just gonna push this. I'm stuck on reloading for some reason. Okay. So do I do not have. So I've got times here, but it's not axiomatized yet. So let's add axioms. At some point, we will want definitions. X times x0. Also, I want actual syntax. Also, I want to change these colons from something. So time x0. So say x times x0 equals 0. Most of the times, x times x sucks times x sucks y equals x plus times xy. Oops, I need to write. I really need syntax for this. Ooh, what? 648? What is this? need proper error management. Indeed I do. Non-exhaustive pattern, time infer intrinsic term. Oh. Did that happen there? Okay. Both of these. Okay. Oh. The proper error management problem is coming on soon on us. What is happening? Same time as plus, that is fine. Time x0. Ooh, yes. Natural numbers. Syntax error. Oh yeah, because it's not for all. It's okay. No problem. So we're going to proceed as with plus. We're going to prove symmetric theorems to these two axioms. I have to think about the termination thing. This is one thing where the function type in in the refined types is supposed to represent total function at that type. We can make a partial function type later. Total functions, I need to be able to specify what it means for them to be total. And I don't know yet how to do this and to be able to manipulate these. Theorem times 0x. Boom. And to prove that times 0x equals 0. And we are going to do that as usual. Oh yeah, I wanted to remove this induction on thing. Where is my induction tactic? Okay. T induction. Yes, okay, it's a proof. Okay. I'm going to do this proof without, and then I'm going to remove the by thing, and if I need it, I'm going to add the suffices thing. So we need to prove that, so we can start with intros as usual. And we're going to prove that by induction on X. Oh yeah, and the ordering bug. And the first is just done. This one is just use times x0 done. Maybe it could have been like by times x0. Be a good shorthand for that. And here, we know that time 0 x equals 0, and I want to prove that for time success. Okay, so first thing we did say is that times 0 sucks x equals 0 plus sucks 0 plus times 0x. That. Oh yeah. Okay. We have that, and we do that using. I could have one without using clause. I'll maybe I add it later, and that uses times x sucks. Still have a syntax error. Due to Alexa error. Ah. Just to check that I haven't messed up all the things. Oh, there's no plus symbol. Okay. What? Okay, it's weird that it prints this way, but no, there's something weird. So this is the goal we want to prove, right? No, that's the goal augmented with our assumption. And so this is, we need to prove that time 0 success equals plus 0. Did I mess up my... Okay. I see. I will need some error messages. Okay. So now I know that have plus 0 time x that I need to prove equal to 0. And so we already know that time x0 is equal to 0. So we can prove we can say that we also have that plus 0 times 0x using equals 0, sorry, using plus 0x, for instance. Yeah, sorry, which times 0x. Now, I have all I need. Okay. So another thing that we could have done is like just proving that, like, interestingly enough, I think that like plus 0, 0 equals 0 would have worked too. No, it's not sufficient. Oh no, sorry, that's just this. So it's actually like maybe better. We don't have to. No, it's just yeah. We already know the time x0 is 0, so we just need to prove that plus x0 equals 0, which we already know too. Okay. So I want to remove this column thing in the induction symbol. Really. So I want to remove this. I'm going to have plenty of... Yep. Okay, I don't seem to be able to go back. Oh, I was already back, I think. That's the reason. I was confused by the green. Okay, so by induction. By induction y plus plus. Okay. Okay, we can look at the induction tactic. Remove the proposition here. Oh yeah, we will have to remove a thing per goal. There will be plenty of errors. So where is... That was called H here. So I have to remove this goal, which I don't care about anymore. And this will be concol. And yeah, there's one too many. This doesn't even track its goals. Yeah, incorrect number of goals, that's normal. Induction, oops. By induction, better. There we go. Simplify induction. Okay, so now we can do our next theorem, which is times sucks x, which asserts that sucks x and y. Okay, I see the problem. So xy is the same as plus y. Oops. I just need to prove it. Go, go, go. Intros. I don't really need id, but so I want to prove times x y equals time. I want to prove that by induction on y, almost certainly, because that's the thing that is usually decomposed in times. Here we go, by induction on y. So now we have two goals to prove this, which shouldn't be too hard. So so now they're reversed, of course. We just have so we know that times of sucks x and 0 equals 0 using times x0. Yeah. We know that times x0 equals 0 using also times x0. So what I'm left to prove that times 0 equals 0. We know plus 0, sorry. We know that using like plus x0, for instance, which is what we wanted, and then we're done. Okay. So we have one thing left. And that's the second one. The other one was just juggling around symbols. Okay. I think I did the same mistake last week. So that today will not be very high improvement thing. A bit of code quality, making things correct instead of wrong, not letting me prove false things. You know, the usual. So, what we want to prove? We know that by induction, hypothesis, sucks x times y is y plus time xy. So far, so good. And then I want to prove that it also holds for success times sucks y, basically, which is a teeny tiny bit harder. Because get plus sucks y, which is sucks yada yada. So now the point is that we want to. So we know that times sucks x sucks y equals plus sucks x success times sucks x y. We know that. I made a syntax. Because I say I should have using times x sucks. Okay. So we know that. Like, in addition to knowing that sucks xy equals plus y times xy, yada yada, something something. So the point is that this bit is this bit that we know is plus y times xy. Okay. Here we'll already miss reasoning modulo, associativity, and commutativity. I'm not sure I want to get bogged down in these sort of details soon. Adding AC to congruence closure is not impossible. It's just annoying. There's no like direct literature to read from. The best I found for that was something called like AC completion. And the idea of AC completion is that you see your equalities as you take a bunch of equalities with some symbols that are AC and some that are not, and you make you make a convergent. Well, it's confluent. Well, convergent, like confluent terminating rewrite system for that bunch of equalities, which in a way you can think of congruence closure as doing as well, except that it just contains it only rewrites the root. So whenever you have a rewrite rule, which is it's the rewrite rules come from the union fine algorithm. So in union fine, every element of a union class is assigned a representative, which is usually has a succinct representation, but is one of the element of this. So this is a rewrites them from elements to their representative, and then you complete by applying all possible rewrite rule everywhere all the time. And in AC completion, you do something similar, you derive a bunch of rewrite rules and you add some rewrite rules to account for AC. That will be confluent and convergent. And so that requires like a bunch of things. And I'm not 100% sure how to do that elegantly in a congruence closure setting. It would definitely be helpful for a proof such as the one we're doing right now. But in a way, it distracts from the point. My point is trying to study the proof assistant itself, and the automation is just to get some things out of the way. But so anyway, back to the thing. Now we have to prove. So we know that this is plus y times xy. And so we want to prove that sucks x plus y plus times. Oh my god. Okay. So the thing is that plus of sucks x and times like this. So this whole thing. And we can sort of write a chain, which is nice. So we have, sorry, is equal to sucks of plus x and this thing again. I really wish I had notation. Okay, using plus sucks x. That worked. And we also know that this by induction, we don't really need to add this. And so this is by induction is plus x plus y times xy. So now we can add that plus x plus y and times sucks xy times xy, sorry, is equal. There's too many parentheses. Okay, there was one too many parentheses, but my editor was confused. This is equal to plus y plus x times xy, but we can't prove this yet. Because we need associativity and commutativity. So we'll need to work that out a bit, unfortunately. So I'm going to keep that for later. Well, anyway, I don't have comments, of course. Probably there's probably a shorthand. So this is equals to plus first, plus x plus xy times xy. And I think that is the reverse of associativity. So I will have to reverse the two clauses. Yeah. Okay. Now that we know this, we have that, of course, plus xy is the same as plus yx, using plus com. And finally, we can do we can say that we can use the associativity again. So plus yx equals plus y plus x. Okay, and plus x. So that's the one. Wait, where is it? Plus y plus x. Right, so now I have plus y plus x instead of plus x plus y. And I need to push sucks y again. I also need, so I need two things. I need to say, oh, but that's actually something I'm interested in. That is times x sucks y. So we're going to have to add this. Except I have to do it in reverse again. Plus, so times x and sucks y is equal to plus x times xy using times x sucks. And so that's all good. And finally, so this is good. And now I need to fold the sucks back here again. And so in particular, so if I do have so sucks of plus y plus times x sucks y equals plus, I need to do it in reverse again. Remove that equal, so this is plus sucks y and times x sucks y. And this is true because of plus sucks x. And I have a syntax error somewhere, which is going to be fun to find. 979 before by plus sucks. Oh, because it's not by, it's using. Actually, the syntax error messages are not bad. I just need to learn to pay attention. Now I should be done, which is not the case. So what's happening? So let's work that again. So this is my initial thing. So sucks xy is the same as sucks time xy. Yes. And this is that. And the same as successor of plus x times success. Sucks y. Oh. No, we have this plus, that can be replaced by plus y times y xy. So this plus x here is the same as this one, and this is equal to this. And finally, this is equal to this because of this. Yeah. So this appropriately proves that plus y plus x, that is that, right? Oh, I see. Okay. Either way, now I should be done. Yeah. That was a pretty long-winded proof for something that trivial. So it's going to be fun when we get to the next two proofs, which are commutativity and associativity. I don't remember which one is easiest for multiplication. So let's start with commutativity, I guess. For all x of type net, I deleted things when I wanted to add things. Where is my colon? Oh, I know what the problem is. for all y also natural numbers times xy equals times yx. Boom. What we can kind of see here is that reasoning up to AC is a gigantic gain. We may also want to just be able to write chains of equality somehow, but I don't know quite how to do that yet. Could just like use transitivity and say and reduce things. I don't know exactly, but like all these can be removed if we have AC. So there. Okay, so we're going to do as per usual. This is probably going to be annoying for the same reason as for the addition, I guess. We do by induction on whichever. So let's say x times 0 equal times y0 is easy. So we have this. Oh. So let's do this. Chook. So have times 0y equals 0 using times 0x, have times x0 no y0 equals 0 using times x0, and we're done. Oops. Worked. Okay. This one is much less fun. Maybe. Oh, actually, it's not that bad, I think. So we have that time. I don't need that extra parent. I don't know. Sucks x and y equals plus y times x. Oh, I see. I think this might not pan out. Let's work our way through it. Plus y times x, y, using times sucks x. All good. At some point we'll have to type check these things as well, which I don't do, and it's bad. That's probably going to come in very important next time. I'm not sure I'm going to have to do any of that, but by the time we use some actual subtypes, which I guess comes at division with this subtraction before. We'll see. We'll also maybe there's a number of things where this can be going next. Another reason why I use the congruence closure is that it forces me to just take decisions that are compatible with it and sort of keep some kind of constraint on what I'm doing. So the other one I wanted to say is times y and sucks x equals plus y times xy. That's very easy actually. Really? No, it isn't. time yx. Sorry. Oops. But we already know that time yx is time xy. Aha. We're still done. Boom! Haha! Fantastic. Okay. I'm going to comment. Comment frequently. You won't regret it. There's a feature in Magit, the Git client I'm using, to just like commit automatically on a web branch somewhere. I've never set it up, but it's just brilliant. Like, whenever you write something after like a second or two, it's committed, and so you never lose any work and always like look at the history of what you've done. I really should do this, but I spend like I do my customizing my Emacs in bursts. Otherwise, it just gets lost in it. Defaults are terrible, and that's sad. Okay, so commutativity of times of multiplication was really easy. Also, one of them is called plus, the other is called times, whatever. Could have been like add and mult. I don't know. I guess it's the reasonable pair. How was commutativity here? Oh, that was similar. Okay, so that was easy. As soon as you have the two lemmas. Theorem times is associative. Shoo. Z, which is also a natural number. And we say, okay, times xy, z equals times x times y, z. What was it for addition? Was it z? That's my natural inclination. Yeah. And so we're going to do the same. By induction on z. So the first thing we need to prove is that times xy 0 times. So that's fairly easy because everything is 0. So yada yada. Okay. Oops. For ID 4. That's just to check syntax. Okay. So we have that times x, y, 0 equals 0, and there's just one too many of these, using times x 0. Fantastic. Have that times y 0 equals 0, using times x 0. And finally, we have that times x 0 equals 0, using times x 0. Oops. Something fell. We're still good, and this should be done. Just to check what's happening here is that we know that this is 0, we know that this is 0, and then we just say that because this is 0, we just do further reduction here. So that was easy. Okay. Now for the interesting bit. So we have this associativity property here. I want to do that for sucks as well. So that's adding z here. Ooh. Do we need distributivity to prove this? Ooh. Ooh. I don't remember that to be the case. What's going to happen here is that we're going to have times xy plus this here. So you can write it. And here we're going to have time x plus of like have x times y plus yz. And this xy and this. So I'm going to write the beginning, but we'll probably have to prove distributivity properties. That is times xy. Sorry, I need to write have. So we know the times xy and such z equal times xy plus what we want, times xy z, which we know to be equal to the other thing we want. And so the other thing that we know is that times x times y sucks z equal to times x plus y times xy. I'm pretty sure there's a I forgot the using times x sucks, using times x sucks just as much. Okay, there's two unproven things, so one of them is wrong. That's the goal, and that is the buggy thingy times x times y xz. Still wrong. Okay. Yz. No. Anyway, I don't need to write time x here, so let's simplify our goal. Oh yeah, that's the problem actually. Okay. It's really very syntactic is the problem. I'm thinking that like using for alls in congruence closure is very similar to using triggers in SMT solvers, and that sounds unpleasant. Or maybe we should just maybe a way to use that is to say that if both sides of the equality exist, like if we found a term that exists and the other side already exists as well, then we edit. Otherwise, we don't. Maybe we just keep it on a sort of suspended thing until the other one appears. There's ways to think about this. Or we just don't do that for everything, but we have some things that we can reason modular for some reason. Or something. I need to explore ideas just to simplify things a bit. Okay, so anyway, so now we know this and that, but what we have as a problem is that we have here we have y plus something in times, and the other one we have So we need to prove the distributivity. So I think I'm going to give it a name when I wrote it. This, when I finish writing it. So we need an x, n. We need like an x. We need 3 values. So let's do this. And what we care about is times of plus times x plus yz equals plus times xy times xz. This, I think this is a theorem, and this has a syntax problem. Yeah, that's times x plus. Let's say this is a distributivity property. Boom. Intros. Induction on Z. By induction on Z. Okay. Okay. Okay, so the first one is fairly easy, as we could expect. The first one, we have that plus y0 equals y using plus x0. And we have oops. I feel there's too many spaces. It's fine. And we have times x0 equals 0 using times x0. And we also know that plus times xy 0 equals times xy using plus x 0. And that should be everything that we need. Error before have plus y. That's a weird way to place the error, if that's the one. No, it isn't. That is mysterious. Let's we have the error. Yeah, we do. I. Okay, that's better. So now we need to prove that x plus y, x times y plus successor of z is the same as time xy plus times x successor of z. That sounds that it might be a challenge, but we'll see. What do we know? We know that plus y successor of z is equal to successor of plus yz using plus x sucks. And we also have, on the other hand, I'm going to, at the other side, we have that plus, we have times x, times x and suck z equals successor. It's probably not going to work. We'll see. Equals x equals plus x times xz using times x sucks and plus x times xz doesn't appear in many places. Now, here we have times of that. So we should say that we also know that times x and successor of plus yz is equal to plus x. Ooh, that's not that bad. And times of x and plus yz using times x sucks. I need a semicolon. Okay. That's what we are at. We have this, which we know to be plus x plus times xy times xz. And on the other hand, we have plus times xy. Ooh, it's just a new AC thing. So this is going to be annoying, again, because of AC, which I'm going to do here. So I know that have plus x plus of this times xy and times y z. Uh-oh. No, that's all right. I thought my computer had frozen midstream. That would be annoying. I assume going well? Let me check. Looks like it's going quite well. Good. And I lost track. Yeah. So this is equal to plus x plus time xy time yz. Oh, sorry. Using what was it? Plus sock. I don't think that's the problem. Whoa. Sorry. Thank you. Wow. I'm guessing there's a parenthesis problem. That is good. That is good. That is good. No, that's fine. Okay, so it was in an inconsistent state apparently. It didn't manage to prove this. Plus x plus there's a time. Twice I wrote time as if times. A very French mistake of me. Okay. So now we do the same juggling that we did the last time. So we know that plus x times xy equals plus times xy and x using plus com. And we finally say that plus times xy x and times yz is equal to plus times xy plus x times yz using plus a sub. And I think we're still good. And finally, we can say we're done. Or not. Okay, so we're not done. Why not? Let's walk through this in reverse. So plus yz equals a sucks thing. That's the one. So this is the successor of plus yz. And so this is more left-hand side, and we say, okay, it's the same as plus x times x plus yz, which is fair. And then we say, okay, we also know that this is equal to plus times x y times xz. Oh, I wrote time yz in a number of places where it should be xz. That's the problem. There's no protection against this. Is that better? It is better. So again, all this is just boilerplate for associativity and commutativity, which is annoying. Okay, so now we can go back to associativity. Well, first we can do the do all of this because it can be useful. So we're going to do x plus x, sorry, and so this will be plus xy z equals plus x times z y times z. And we're going to prove that purely by commutativity. I think. What do I want to prove? So plus. So I can do. I have that times plus xy z equals times z plus xy by times com. I already have a syntax error before by because it's using the Grenier. Okay. That's one of this thing we want to prove. So we have z times, then we can do have times z plus xy equal times equals plus times z y and times zx, sorry, and times ny using times x plus yeah, still good. So we also have that times zx equal times xz using times com. Have a second one like this with y. So y, still good. There's a lot of red crosses, but it's exactly how it expected. And finally, we say that plus. We also have that plus times xz times yz equals plus times yz times xz using plus com. Oops. Should be done. Here we go. Okay, that was just for convenience. Okay, so we're back here. So we have proven or proved or both that this is time x plus y xy. So I do have to say that we know that time x plus y times yz is that the what he proved? I'm confused. Oh, that one, yeah. Yeah, so that's the 1 plus 1 equals plus times xy times x times yz. Syntax error using times x plus. Is it done? It might be done. No, it's not. Oh, wait. There's something that doesn't work here. He can't prove this for some reason. Spacing the parentheses is weird. Time x plus y and z is time yz. Time xy times z, time x times yz. Oh, there's a time without an s. Now that is okay. Are we done? Probably not. Yeah, we are. Okay, great. Okay. Well, we know everything there is to know about times now, I guess. On its own. Now, what do we want to define? What's my next step? What's my end goal? What do I want to prove? What do I want to work on? Actually, I say that, but like, what's the right conventional commit for this sort of thing? I didn't add any feature really. Well, I did change a couple of things, but fix feet. It's not very important. Feet. Theorems improves on natural number multiplication. It's a bit pretentious. Okay. Well, the real question is, what do we want to prove next? There's a couple of things that can happen. So we can talk about the truncated subtraction. We could talk about the non-truncated subtraction, but whose second element has a type depending on the first one. Which I actually cannot do right now because there's no dependency. We could add that next. Oh, that also should go. Should have gone a while ago. That actually commuted, so I can, oops. That's not what I wanted to do, but it's fine. Pair. We could do division and start thinking about it. I don't know what to prove on division though. We could repair this temp axiom though. Because it doesn't say anything right. So division is such that if 0 is different from m, and p is times nm, and n is div pm. Actually, that looks correct. Though it should be an equivalence, right? Maybe there's a better. Well, actually, that looks correct. No, actually, it doesn't define what dpm is if p is not divisible by m. Well, that's the problem. Um, so a route characterization is something like a Galois connection of sorts. Isn't it though? I think it is. I want to say that we could also return a pair and define the actual Euclidean division. But you can define division directly, I think, and characterize it as being a Galois connection with times with respect to the natural ordering, or something like this. Um, so I don't have equivalence yet. I kind of need to add this. So there need like there needs to be some value here. So that like plus k equals should be read as the and should be an existential as well, which we don't really have a way to figure yet. Yeah, that doesn't type. And that should be an equivalence. No. Well, that was correct, but it doesn't exist. Okay. Yeah. Is that correct? Like a like the product of nm is smaller than a p if and only if n is smaller than the division of p by m. Is it correct? It probably is. Like first, when k is 0, so when nm equals p, m divides p, then this is actually a definition. Is correct. If I take p plus 1, just like p is 1 more than a divide than a multiple of m, then dividing p by m will get that is the same value as dividing the multiple. So p minus 1. So like this is a plus 1. We say this n. It's not the same k. First, that's a mistake. Oops. I think that is true. It's becoming a bit annoying, so we'll want to compact this eventually, but it'd be also nice if we could just express this. Okay. Let's make a plan a bit, and probably we'll leave it at here because it's pretty late and it may not be the right time to start with this. Um, yeah, I think it's pretty clear that is correct, and it's a complete specification. There's just one function that can do that. So this is pretty nifty. That is nice. So what do we need? Or what would I want to prove with it? I don't want to do some Galois connection math right away, proving that this is a complete characterization. But I want to do some proofs about division. What is true about division? Um, like we're going to have some kind of inverse theorem, like, you know. We'll need a real name. For all n MP, so all are natural numbers, and I need to learn how to type. For all m, also, you know, just copy things. I'm very slow. And we'll say that p is not 0. I'm going to put this in order as well. Here too. These were reversed just to check the congruence closure mechanism, but p equals 0. I need this, and then I can say that times. Well, I could just say that p is, and yeah, I can say that. Oops. Is part of the natural numbers. That neg p equals 0. Oops. So we can remove this, and it's just, there's no condition per se. It's just part of the typing thingy. This also is going to be interestingly challenging for congruence closure. Well, not really, because it's just, yeah, it's fine. It shows that grounding is not easy in any way. So times nm divided by p. Oh no, I didn't need the p. I really need m. Equals n. That's an interesting theorem to prove. I can prove it with this as well, which is this. So there's an axiom div exact. Oh, div of multiple. Yeah, I say. Or div by divisor. I'm going to do the same. Say that m is a non-zero we'll need the ability to give a name to these at some point, which is not as obvious as it sounds. So this, okay, we can actually, oh, that is fun. We can actually prove it was just this one. This one should become a theorem as well, but we can prove the other theorem was just that because it's the case of this. And already we'll have some things to change because we need to prove some. We can write wrong things already. Okay, so we can do have n. Yeah, but I say we can, but I need to be able to think about implications. So I think that's the plan for next time. First is let's add implicative reasoning or conditional reasoning of a sort or another. Because I want just to be able to use this. The point is that so if I do associate p with times nm, of course, like this and this mean exactly the same thing, but they're presented slightly differently. It's not like fantastic mathematics. Whatever. it's, it's really not. But it sort of tests. I need to be able, in a way, to prove that these two things are equivalent. At some point, something like that. So this is an instance of this, I think. So this is an instance of this. I'm pretty sure it is, though I'm not exactly sure how trivial that is right now. I'm going to remove this as well and put it in the types. Using my mouth, not using my mouse. It's an interesting mistake. I'm not sure why I have m different from 0 twice. Every time. It's actually wrong. So already we can see a couple of things. No, that is correct. Like it's trying. Okay, that's correct, but that isn't. This is no type checked. The context where that makes sense. This sub goal appears when you do this. It just checks that this m is different from 0. It gets it from the context. However, I have no idea where these come from. Okay, so we might have a look right now because we might be able to fix this, and that would wrap up the night pretty nicely. So let's have a look about why these things are happening. I think I'm figuring it out. So first, some stuff about diff. Okay. Damn. So when I do given okay, so that's not emit, that's the given. Where, how do I do assume? Okay. So what's happening? We'll also figure out why we have two of these, whereas I think that we should have a single one. This one also has two. It's quite interesting. So we're doing type. We're doing a preposition. Well, let's start with this one. No. Oh yeah, I've seen an implication, so I've assumed it. I've done something else again. Ooh. So there's assume and there's emit. Emit just takes all the givens and something. So the problem here is that the givens are definitely not well scoped. So when I find something, I go out of that scope and it stays there. But really, assume should be local. We actually don't want assumptions to exit our environment. I'm not exactly sure why the givens show up here, but you know, there's a couple of things. So we don't really want the things to escape their environment. Even if they're bound, they're not bound. Like you have a for all, blah blah blah, and you have an implication here, and this implication doesn't talk about any of the for all, so it's completely like general, and suddenly it becomes part of your assumptions. But you have it here too, so that is wrong. It's really when you open this that it becomes a given. So we'll have to track the assumes. But let's have a bit of a look. So we're type checking the preposition. So we go through a for all. I will assume anything. That is a good start. Okay. Okay. So we just added the thing. Why not? Might not be the right thing to do, but why not? Um, and so we just walk through the fall, we add the thing to the environment, and we get to this equation. And so we do type check, type infer refinement term, we'll get the variable, we'll say, from the type of the variable. Then we apply the variable, we say, okay, we check the comp arrow given of f. Not a refinement term, E type of argument. So here we check that M as type N. Assume, here we go. That's the reason. So we assume the constraint type of E. We omit the constraint TE. How many instances of assume is there? 3. This should probably very, very, very much be scoped over Q relay. I was right. So because it's scope, it doesn't need to be state, so I can change that into some reader T of prop. So here it becomes ask p true of act is act. Also that's a p equals local p colon. Yeah, okay. Okay. I mean, just refer it. No, save. Okay. Revert. Yes. Dante enabled. Here we go. Assuming. Oops. Already. Okay. Well, I'm not doing this again. Assuming dollar. Do is missing. Relay. Boom. That is just run reader T. Okay. We don't use minus T anymore. Fair. And now, what do we have? A single occurrence of the given that needs to be proved. Here it is there, and it's proved, and here it's not here anymore. We fixed the bug. Fix given constraints don't escape their scopes. We can like already rearrange that. So this will be, I'm going to make a new branch here. And I'm going to call it find slash implication. Just checking it's upstream. Is origin refine implication. Refine interactivity. It's in the same is back here, which is exactly what I wanted, I think. Yeah, okay, that's exactly what I wanted. So we're going to make a pull request with this one. Add basic interactive proofs. There's actually no CI. So it is just for the sake of it. And we can just merge. Boom. And that will be it for me tonight. Lest I forget to sleep tonight at all. So next week, it is going to be a case of video gaming, and as I mentioned last week, I'm not in the mood for like working on things or learning new things or practicing. So it's probably going to be a rando, probably a like overword glitched seed so that I don't lose the practice. I don't forget. And I'll be back in 2 weeks on this, where we will be dealing with implications. I have a bit of design to do, and I need to think about it a bit more than I did in the past 2 weeks, where my mind was totally somewhere else. So I'll be thinking about it, I hope, and we'll resume here. There is not much to do in the meantime, I think, apart from thinking about the design and the and how to deal with implications in a nice way in this setting, which might like be an interesting rabbit hole. Little by little, everything that doesn't bring me closer to quotient is good now, because I'm so terrified of quotients. And maybe this will turn out to be misguided. There's another thing that we can do is also add dependencies and add existentials. All these things will come in handy. Equivalence, we'll see. I am not entirely sure how I'm going to do all of this. So plenty of design to do. And so if you come back in 2 weeks, we'll have more discussions about this. Like I might even have something interesting to say. Also, this is ugly. But this is the consequence of not having to write any printing code. Like the total printing code that I wrote is like 10 lines long. It's pretty good. So back on track. Yeah. So I'm gonna think about more provy thingies next time. So the potential things are existential implications and something else that matters, but I forget. Um, and set that up, hopefully. So we'll be sure to tune in and have a conversation about how this turns out. In the meantime, if you've been following this, it's always a pleasure to share these moments. Um, and I wish you a good night or a good day or a good whatever time it is where you are. I'm going to cut stream now, and until next time, stay curious.